So we know we can make row operations happen by multiplying on the left by what we're calling elementary matrices. And the elementary matrices come in three flavors. Elementary matrices that do a row switch, elementary matrices that scale a row, and elementary matrices that add a multiple of one row to another. Incidentally, this off-diagonal constant that you get for this case, it might be below the diagonal depending on whether you're adding a row to a higher row or to a lower row. So this constant might be down here depending on what you're doing. So now that we know about these elementary matrices, we can actually come back to the question of doing row reduction. So what is row reduction going to look like if we have elementary matrices? Well, so here I'm using e's with subscripts to represent elementary matrices corresponding to row operations. If we have a system of equations represented by this matrix vector equation, ax equals b, we know we can solve this by doing a series of row operations. And this series of row operations has a corresponding series of elementary matrices that do those row operations. So what we can do is take this equation, multiply both sides on the left by the first one, the first elementary matrix, whatever that is, E1a x equals E1b, and then do the second row operation by multiplying on the left by the second elementary matrix. So then E2 times E1a x equals E2 E1b, and so on until you get to all of them. So ER down to E1 times A times X equals ER down to E1 times B. And at this point, you would be done. Well, at this point, what would the augmented matrix for this system look like? Well, the augmented matrix is, right, this is the matrix part. So the augmented matrix would be ER down to E1 times A. And then the last column, the augmentation column, is this vector, the vector you started with, but with all of the row operations applied. So ER down to E1 applied to B. But if we're finished with row reduction, this matrix here will be the reduced row echelon form of A. Because, I mean, that's what we mean by, that's how we tell when we're done doing row reduction. We're done when we get to the reduced row echelon form. So when we do all these row operations, the reduced row echelon form will appear right here. But notice that what we have now is we have the matrix that we started with multiplied by a bunch of elementary matrices, and what we get is the reduced row echelon form, which maybe we could call capital R, I guess. So what we're seeing is for every matrix, right, no matter what matrix this was, if we multiply on the left by a series of elementary matrices, we can make the whole product be the reduced row echelon form of any given matrix A. So this is a really nice way to sort of realize row operations and row reduction of a system as just multiplying by a bunch of matrices. Also, it sort of gives us some insight into sort of how A is put together, right? Each one of these, we know from before that every row operation, the opposite of it is also a row operation. And so if we can multiply on the left by all of these matrices to turn A into R, that means it's possible to multiply on the left by all of the operations that undo all of these. So for now, I'll call these dr down to d1 to get back to the matrix A. So this sort of displays the matrix A. It decomposes the matrix A as a reduced row echelon form times a bunch of matrices that we'll see that these matrices, first of all, they're elementary because they represent row operations, but also they have another nice property which I won't mention right now, but will turn out to be important.